Welcome to my presentation. My name is Cornelia Wulff. I'm from the Technische Universität Dresden, and I would like to talk about the virtualization of reconfigurable mixed criticality systems. Virtualization enables the joint execution of multiple guest operating systems, isolated in virtual machines on the same hardware platform. In embedded systems, often general-purpose operating systems, for example for the processing of large data amounts, run next to deterministic real-time operating systems for safety or security-critical control systems. FPGA virtualization provides guest operating systems with reconfigurable resources, raising the challenges to guarantee isolation in two respects. Data isolation protects from malicious applications and untrusted users, and performance isolation ensures that applications in different virtual machines do not affect each other. In particular, non-real-time applications running in the general-purpose virtual machine may not affect real-time applications. In FPGAs, the context switch between hardware tasks is much more tedious than on processors and can be associated with high reconfiguration latencies. State-of-the-art works tend to isolate subsystems in spatial respect at the expense of lower resource utilization, or restrict their system to one real-time operating system next to multiple general-purpose operating systems. We propose a virtualization layer called L4REC, which adds FPGA virtualization to the microhypervisor L4RE. Our main contributions comprise a mechanism that isolates hardware accelerators. In order to offer a high-level programming interface, we extend the POSIX thread-based unified hardware-software execution model introduced by Reconos by periodic threads, which is a typical use case in reconfigurable embedded systems. And we present a dynamic mapping and scheduling strategy for hardware threads that considers different real-time levels: hard, soft, and no real-time. Objective of the strategy is to increase area utilization combined with deadline compliance. Guest operating systems use virtual FPGAs, which are abstractions of the physical FPGA, and can contain an arbitrary number of hardware accelerators. To inhibit unauthorized access to hardware accelerators, we use the I/O server that L4RE provides to handle all platform devices. The I/O server gives each I/O client access to a set of resources attached by a virtual bus. The L4REC backend driver obtains the right to access the complete FPGA, while direct access is prohibited for virtual machines, and communication is only allowed via virtual buses. Any application that tries to access the FPGA directly receives a page fault exception. We offer a high-level programming interface that supports periodic and aperiodic threads. The functions pthread create and pthread join for creating as well as joining threads and reading their results have the same signature as the functions in the POSIX threads library. They only differ in the type hardware thread that stores the required hardware accelerator, worst-case execution time, deadline, period, and real-time level. All instances of periodic threads use the same hardware thread variable, but different input parameters. A software function can be passed that is called when a hardware thread cannot be scheduled to the FPGA. We add further functions to reserve an accelerator prior to its use in order to mitigate DBR latency, and to delete periodic threads so that they are only executed for a certain duration. In our L4REC mapping and scheduling strategy, thread instances have the state running on a hardware accelerator or waiting. Real-time thread instances in the ready queues are ordered by deadlines, and non-real-time thread instances are added in the idle times that arise between periodic thread instances. We distinguish 5 scenarios. In our example, we assume that a thread requests execution at time unit 1. In the first scenario, a reservation for this thread exists. The thread instance takes the place of its reservation, In case of a periodic thread, a further reservation is added and the schedulability is tested for the ready queue. In our example, the reservation cannot be inserted at the desired time unit 10. It is pushed to the reschedule queue and will be rescheduled to PRR2. In the second scenario, no reservation exists, but a PRR that holds the required accelerator and has enough idle time so that the thread's deadline can be met. If scenario 2 does not apply, but an empty PRR exists, the required accelerator is loaded via dynamic partial reconfiguration. If the DPR latency is so high that the deadline can be missed, it is exchanged with a thread on another PRR with the same functionality and a lower real-time value. An overload situation is given if those PRRs that hold the requested accelerator have not enough idle time. If suitable threads with lower real-time value exist, they are pushed to the reschedule queue to make space. In the last scenario, the required accelerator is not available and has to be loaded via DPR. Now, the reconfiguration time has to be added when searching for a suitable space. Threads that cannot be rescheduled are moved to the reject queue and are executed in software instead if a matching software function was passed in the pthread create call. Otherwise, rejected threads have to wait until a PRR is idle. If these are real-time threads, the system is overloaded, which might lead to failure and should be avoided. We evaluated L4RAC on Xilinx UltraScale Plus MPSoC using 3 para-virtualized FreeRTOS instances as guest operating systems, 1 for each real-time level. And on the FPGA, we set up 4 PRRs that can be equipped with 3 different kinds of hardware accelerators. We synthetically generated hardware threads with random values for the accelerator, execution time, period, and deadline. We compared our strategy with an existing strategy that orders hardware threads by deadlines and uses the same mechanisms to reduce DPR latencies, but does not distinguish real-time levels. Our strategy executed 36% more thread instances than the EDF strategy because non-real-time threads are inserted into idle times. L4RAC reaches a utilization factor that is 1.9 times better than that of EDF. The average values of the utilization factor are marked with vertical lines. The last diagram shows the overhead induced by our mapping and scheduling algorithm, broken down by the 5 scenarios. The most frequent scenario, the search for a reservation, takes less than 50 clock cycles. We presented the FPGA virtualization layer L4RAC, which enables the shared usage of reconfigurable resources by several guest operating systems with varying real-time requirements. The L4RAC strategy reached an area utilization that is almost twice as high as that of an existing EDF-based strategy. Several improvements are left for future work. The cooperative scheduling scheme could be changed to a preemptive one. PRRs could vary in their sizes. And finally, the scheduling could be adjusted to the availability of the processor configuration access port. Thank you very much for listening. I'm looking forward to answer your questions at our poster.